Hey everyone, and welcome again to another one of our excellent sessions on machine learning. Hi Jason, you back with us again? Good to see you.
Glenn, good to see you as well.
Excellent, and we've got a lot of stuff to go through today. Thank you everyone for coming back. Wherever you are in the world, feel free to reach out and say hi and tell you where you're dialing in from. We'd love to know. And we've got a great session today, Introduction to Data for Machine Learning. And what we're going to look at is a few things. Actually, let's go and see where we've come from and what we're going to be doing in today's session. So many of you may not know Jason if you're just joining in. So Jason, would you like to introduce yourself to the world as well?
Yeah, hi, I'm Jason. I'm a Cedar product manager here at Microsoft. Specifically, I work on the AI and ML content, which in that role, of course, I had a little bit of a hand working with our amazing authors on creating the learning path that we'll see here. But of course, the authors, the coders who did all these exercises deserve most of that credit.
That's true. My name is Glenn Stevens. If you've not met me before, I'm a senior content developer here at Microsoft as part of the Learn Live team. And excellent. I can see on the screen we've got our schedule of where we actually come from already. This is the third in our series of 9 that we're doing. The first 2 episodes we've already done, Introduction to Machine Learning and Building Classical Machine Learning Models. And that's been fantastic. And today's session is we're going to look at data for machine learning. And data is a pretty important process because it's actually our core input to a lot of the things that we do. Right. So we'll be going through that. We'll leave the details as we go through. And there's actually plenty more. There's only 2 more displayed on the screen after this, but there's actually another 4 after that. And there's lots of great content to go through.
That's right. We're not even a third of the way through. By the end of today, we'll be a third of the way through, right?
Yeah, excellent. That's true. And we've just seeing some people messages as well. We've got people calling in from LA, New York City. Look, we've made it in New York City, so we can make it anywhere. That's amazing, Jason. I think it's New Hampshire as well.
Sometimes I call Glenn old blue eyes.
A little bit, but my eyes are brown. That's wonderful. It's great. All right, well let's keep moving on, and we've got some people from Australia as well. And cool. Now, I also want to mention that at the very top of the page, we've got our link to our learning path that we're following for this, which is aka.ms/learnml. And if we just go to our next slide, you can actually see the individual link for the module that we're working on, which is aka.ms/learnml-data. And that's the core work that we're looking at today. So we're actually going to follow along with the module that's being displayed on the screen, but we're obviously going to talk through it from our point of view as well. Jason has a lot of experience with machine learning, and we've got some excellent moderators on the line as well that'll be able to help you out with this. We'll get to that a little bit later. But what's the core things that we're going to look at today, Jason?
So today we're going to look at how we can understand our data. And specifically, this says visualize large data sets. Of course, we've got our hands-on elements of our Learn Live sessions. We're not really going to be working with a very large data set because the reality is we kind of have to do it real time for you. But we're gonna work with a data set that's large enough, 900 or 1,000 records, and it's large enough that we're still not going to bring up all of the records on screen and just kind of eyeball them, right? And that's really the key point, is once you get past that state of eyeballing, you start to have to use sort of some statistical analysis techniques and things like that to understand your data. And once you understand the data that's coming in, you almost invariably are going to find that there's some problems with it. And this isn't really unique to machine learning. This is anyone who's done any kind of development with data, with a SQL server, with a Postgres server, right? I mean, if you've worked with data, you know that a lot of times there's some junk in there, and it needs to be cleaned up. So you need to fix it. You need to do something with it. And that is what we're looking at today, is how to deal with and fix data issues and get our data ready for a really good machine learning program.
Awesome. Now, it's also worth mentioning we are live and interactive. We're seeing a bunch of questions coming through. Thanks everyone for letting us know where you're coming. That's awesome. There's even a note there from Nate. Jason, it looks like you've changed your wallpaper color. No?
Is that something? Oh, back here. Oh, I added an extra light in the room. room so that hopefully my camera coming in better, and it probably makes the paint color look different. I thought you meant my desktop wallpaper, Nate.
No, that's really good. Well, it shows that people are paying attention, Jason.
That's right.
That's what we like to see as well. Awesome. So moving on, we've got a bunch of moderators. Jason, you've actually worked with some of these in the past, right?
These folks are amazing. I tell you what, the people who are answering questions in our chat for all of our chat channels. Of course, we hope most of you are watching on Learn TV, but we're simulcast on a few other channels as well. So wherever you're watching, we have some chat moderators, some people working there. These are our Microsoft people who are experts in machine learning, experts in data analysis, and they're going to answer a lot of your questions. We're hoping that they'll float a few of those questions up to us as well, because it's fun for Glenn and I to answer occasionally. But yeah, these folks are amazing. They're in all of our chat channels, ready and waiting to help you out.
Cool. So let's get into the core content today.
Yeah, so as we mentioned, we're going to be looking at our data sets and how to make sure our data sets are ready to do good work for us, or at least with us and our machine learning models and training. And when I think about preparing data, I'm reminded of when I was a small child in the mid 80s, and I'd go into my mom's work, and they had, of course, the big scary looking computers there, but there was a sign with a sad faced computer above the computer there, and it said garbage in, garbage out. And I know we've all heard that, but that's been around for that long. It was, this we're talking about early to mid 80s here, and we're still saying it. We're still worried about it. We still need to fix the garbage, right? So that's what this is all about. Machine learning in particular is sensitive to this, right? When we talk about it in old school algorithms, if you put garbage in for your particular problem, you're going to get garbage out, sure. But with machine learning, if you put garbage in on a training set, you're screwing it up forever. You're never getting an optimal answer for any problem, for any individual record that you try to throw against that model that you trained with bad data. So it becomes all that much more important. And we're going to be, I won't say diving deep today, but we're going to be touching the surface of the most important techniques. And beyond that, we also have some links for further learning if what you really want to do is focus on data analysis, data cleansing, and work with data. We've got some great, I'll say, sort of a detour learning path that'll take you off the machine learning path and let you dive deep on data analysis. So we'll get that to you at the end of the session. Glenn, you want to tell us about our scenario today?
Right. So this is interesting. We've got some data from the Titanic, like from the 1920s or whenever it launched. But we're trying to find out the kind of how much someone would be likely to survive if they went on the Titanic. And we have some data, like we have data on things like how much they paid for a ticket, what's their age, some siblings. We don't have all the data. And in fact, that's one of the core problems. We've got some missing data. Like we don't have some of the ages and a few other things. Like we don't have if they were on a door, for example, on the Titanic. We won't reference the movie at all, but it's the lack. That's right. But there's a lack of data that's going to tell us so we can calculate what's the percentage that someone might have survived that trip. And because we've got some sketchy data, we need to do some cleanup in a few ways. And we'll look at that process, because you'll find that if you're working with data, you're going to have some missing data as well. And like as Jason said, if there's garbage in, you're really going to affect that model in negative ways. So we need to fix that up and clean it. That's what we're going to be looking at.
Fantastic. So good, bad, and missing data. I think both Glenn and I have kind of hinted at all three of those things at this point. So once again, we want to focus on the fact that machine learning gives us its power through the data it gets. Now, of course, we're gonna select model architectures. We're going to select what we call hyperparameters. We'll learn about that in a few more modules. We're going to have some tweaks and levers that we as ML engineers or data scientists can use, but we need good data. In fact, cleaning up the data and making sure that the data is good is our greatest lever. That is the greatest thing we can do to improve our models. So the first thing we want to do with our data set is make sure that it's representative of the, well, I'm actually going to use the jargon that's on the slide, and we'll work on making sure that we thoroughly explain each piece of that jargon. But we want to make sure it's representative of the population that we're trying to model. So when we say population, we're referring to every possible data point or every possible example that exists in the universe. So if I want to predict if someone's likely to buy a car, then the population might be anyone who might ever consider buying a car, which might ultimately be darn near everyone in the world. Well, not everyone in the world, but you get the point. Our population is every possible data point. Right now, we don't ever have every possible data point. I don't know what cars every single human in the entire world has looked at, has test driven, has purchased previously. I don't have all that data for every single person. What I have are samples. And so the sample is the data set that we have. The sample is, I may have hundreds of thousands of records for individuals and what cars they've owned previously and what cars they've test driven. And that would be my sample. Hundreds of thousands is a lot, but it's still not the entire population, which is millions and millions. So we need to make sure that when we get our sample, our hundreds of thousands of records, the absolute very first thing we need to understand is, does it represent the entire population correctly? If it doesn't, if it has more men than women, if it has more old people than young people, if it has a certain type of man, but a good sampling of women, any of these kind of skewings of the data can mean that we're going to get a poor result. So that's one of the things we need to do in our data analysis, is understand, are we representative of the entire population?
Yeah, that's some really good. Yeah, well, that's a really good point. It's like if you've got a million people and you've only got 1,000 people in your sample, you want to make sure that 1,000 people represent the kind of spread of people in that million. That's what you're really saying, right, Jason?
Yeah, right. I mean, there's some simple ways to look at it. If 40% of your population is over age 60, then you would expect 40% of your sample to be over age 60. And if it's not, you might have to wonder if you've got a problem there. And then of course there are ways to adjust for such problems, but you need to understand them first.
Cool.
Now, another obvious issue, and this one probably is more obvious, is data error. Now, I made sure we have a jargon warning down at the bottom, because I want to make sure that you understand when I'm talking about error right now, data errors, data problems, we are talking about the garbage in. And this is more of a classic definition of the term error than what you've heard me say in these sessions before, because unfortunately, again, confusing jargon warning, unfortunately, it's a bit of an overloaded term. We use the term error interchangeably during training with loss or cost. And I don't mean it that way here. When I say data error here, I mean, make sure your data is not wrong. Make sure somebody didn't put the wrong value in because your data entry fields weren't ideal, or because your importing process wasn't ideal, or whatever it was. Make sure you've got good data.
Oh, like someone missed a decimal point, for example, and there's some problems there. Yeah.
Yeah, exactly. You've got that data entry field that just lets people go typing away, and if it doesn't have any validation, then maybe you said that your car costs $40 million instead of $40,000, which, I don't know. That's a heck of a car. I'll take that car, but only for free. All right, and then finally, we want to look at missing data. So data could be missing in a few ways, and one way is to think again about kind of representation, right? So what we've done is for Tom here, we've kind of grayed him out to represent the idea that even though we expect data for Tom, we maybe didn't have it. So of course we can have missing rows, incomplete data, which would make it non-representative. Hard to generalize based on data that only represents a small subset, or a certain subset, even if it's a large subset, right? The other thing is, of course, within individual fields or individual columns, or of course in machine learning, we call that features. Within individual features, we might have some missing data. So Reese here doesn't have his height listed. though he does have his weight listed. Again, that is going to impact things. There are different ways, as we'll see shortly, that we can handle it, but we need to understand it first, and then we can look at mitigating.
Yeah, cool. And we're going to have a look at it. A demo, yeah. I think we're on the same path there, Jason. But yeah, we're going to look through a demo and actually talk about and execute some of those concepts we've been discussing, how we can prepare data, how we can look at missing data, what to do with it, do with that missing data as well, and the steps you can take. Because like you said, or like the previous slide showed, there's actually a few options we can take, and depending on what's happening, we have to choose the right answer for the right context. So let's switch over. I'll just share my screen.
Please do.
Yeah, and hopefully everyone can see that now. I'll just move your window out of there as well. And we've got our exercise. We're following along with the Learn module. Like I said before, this one's we're going to look at visualizing missing data. And hopefully you've activated your Azure Sandbox in there. One of the nice things about these modules that we're going through is they're running with Jupyter Notebook. So you don't actually have to install anything. Everything's executed for you in the browser. It's talking to some Azure services we've got set up for Microsoft Learn, and you can just step through it in the same way that we're doing. Or you can just listen, follow along, and do it in your own time a little bit later.
Yeah, of course, these modules are always available to you at those links that we provided you earlier. Again, the aka.ms/learnml will take you to the entire learning path. And I think this one was aka.ms/learnml-data. And you'll come right to this module and be able to go through this code, again, with no install or concern or worries or effort other than thinking and learning. You'll be able to go through this module in your own time whenever you want.
Awesome. So remember back to our scenario. Our scenario is we're going to look at the data for the Titanic survivability log, essentially. So we have some data, and we'll look at that data as well as we go through. Remember, garbage in, garbage out. We want to avoid the garbage going in, so we want to see what we can do with that data. So the first step here, I'll just execute this, is what we're going to do is essentially look at the Titanic CSV file, go through that structure, and just take a look at the head. So the head method is a pandas method that lets you look at just the first 5 rows of the data. So let me scroll down here, and we can get a sense of the shapes and the columns that are there. So we've got a passenger ID, if they've survived or not, the P class, which is like the class of ticket, the name, sex, age. I think we've got details on if they have siblings, and there's a range of other things like the ticket, the fare, the cabin, and embarked.
Those 2 columns right there are really odd. And remember, sometimes we're not in control of what data we get. So that SIBSPA, that's sibling or spouse. So right. Did they have a sibling or a spouse on board with them? And then the other one is parent or child. So PAR or CH. So parent or child. So I can't begin to understand why the data is collated this way, to have a sibling or spouse field or a parent or child field.
Yeah, you know what, Jason? I think in the early 1900s they weren't really thinking about machine learning when it comes down to it. But
that's certainly part of it.
All right. So if we have a look at the data and see the amount of samples and columns, there's actually quite a lot in there. You said about 900 before, just a little bit shy of that 900 mark, 891, and there's 12 columns within the data as well. Gives us a nice little sample to work with. But at the same time, data collection processes weren't efficient, and they had imperfect data, to be honest. And in the case of a disaster like the Titanic, there's bound to be some missing data as well. So there was more than 2,000 people on the Titanic, so we don't have the full numbers, but we want to assess really what the missing data is there in a little bit more broader sense. So this code here, what we're doing is we're looking at the data set, we're getting the values where it's null, and then essentially grouping that data so we can look at the column structure to see which particular columns have null values.
You know, it might be instructive if you could just grab that dataset.isNull and then the parens and just paste that into another code block real quick, and just show the folks what we get.
Underneath?
Yeah.
Just the isNull? Yeah. Sure.
No, yeah, just right there. Yeah, exactly that. Because I'd love them to see what this does. And basically, we're going to get,
and
no, just we don't need a variable.
okay.
You had it. Yep. One of the nice things about Jupyter is it's going to automatically print it if it's the last command. So notice that we actually have an output for every single cell. But now, instead of having the value of the cell, all it's doing is telling us whether that cell was null or not. So now, when we see what Glenn had up in the cell in the whole code block above, where it says sum, it's summing up the columns and saying, okay, how many have true? Because, well, true cast is a 1. And so we can see that age has 177 nulls.
Cool. And Cabin's has a bit more damage to its data structure. And a very small amount unembarked. Okay. So that's showing us the sum of data. We've got 177 passages, that didn't even embark, and cabin information for 687 people are missing. So that's a fair chunk of data that we've kind of got to work out a strategy of what to do with. All right. And so that's going to get us to the next step, where I think in the previous 2 sessions, we've talked a little bit about visualizing the data so we can get a sense of what's actually going on. So if you look at just raw data, sometimes it's hard to group that and structure it in your mind to go, what's actually happening? What's the trends? And this is another little technique that we can use here, again, where we can actually go ahead and use this library here, the MSNO, or the missing number, and then actually draw a matrix of all the columns and show which columns have data and which don't. And you can get a sense of the missing data just from this image here. So things like the passenger ID, survivor, P class, name, and sex, and so on. These ones that are just solid, they have essentially all the data. But the ones like age and cabin, they're missing some data in the process.
It's a great time. Glenn, you brought up that we've talked about visualizing data, and we started to look into another example here, but it's a great time to mention there are so many different ways to think about visualizing data. We're going to look at a few of them today. I know that there are a few you and I even chatted about that we didn't include here today, and who knows, maybe we'll end up talking about them if a question goes in that direction or something like that. But there are just so many. There are so many different ways we can slice the data, look at the data, create a visual for it. And so we're only going to touch on a few of them, but by no means let that restrict you. If you let it inspire you, but if you start to feel like you have an intuition of a way to put that data, a lens against that data, do it, look at it, try to get that lens, try to get that visualization that sort of inspires you.
Cool. Yeah, it's a good point. The more tools you know, though, the better you can do things as well. Be creative. Nice. So we have this age and cabin missing data, and the next step is we want to actually start to get a look at what that data is, where it's got the information missing. So we've got another pandas data set that we're creating here, where we're looking at the data set and we're looking at the values where the age is null. So that's essentially creating a Boolean mask there against the data set, and then printing out the details of the unknown age, but just showing a few of the columns: passenger ID, name, survived, and age. Let's go ahead and look at that. And we can see the age there. It should only be 20 records in that display.
And we should have all null ages.
Yeah, which we do.
Oh, and we should mention, it says not a number, doesn't it? It doesn't say null. It says not a number. Well, okay, that's a pandas thing. For the most part, there are some very, very, very nuanced subtleties to this, but for the most part, pandas treats null, not a number, not applicable, none, all those values as the same thing, even though it actually does have definitions and constants for each of those separately. It essentially treats those as the same. And so that's why that value is null. It prints as not a number, but if we did is na, it would show as true. It essentially treats them all as the same thing.
Right.
We did is null.
And I've certainly worked with data for a long time, and often you have to correct the data as well, and just someone might actually type in a string and go n/a in that string, and you have to compensate for it. It's
That's
quite
true. That's not this case. This case, that's just
no. There's plenty of others,
it's
but we could do the similar thing with not just the age, but also the cabin. So we'll use that pandas process again. So in the previous one, we're just using the dataset age essentially as the filter, but we can do another rule essentially where we're missing the age as well as missing the cabin. So let's go ahead and run that cell. And it's just showing the number of cells where it's missing both in this case here, which is 158 cells, 158 rows, I should say. So most passengers missing age information, also missing cabin information. That's the
yeah. If we just look at that real quick, we can see that I think it was 177 missing age. So of those, 158 are also missing cabin, which isn't surprising. 70% of our records are missing cabin, but it is at least useful to understand that intuition holds true. I guess that if it's missing age, it's missing cabin as well.
Cool. So we want to understand why we've got that issue. And so likely it's because those people may have just bought the tickets that you can just buy and walk on rather than the people who might have bought like the different classes of tickets. So what we want to do again is do some visualization. So we're going to show the graph essentially, or the visualization for all the passengers, and then for the passengers that are missing the cabin and age details. So if we look at that structure, we've only got a few rows here. I might actually zoom my browser slightly down so you can see both on the same page. Yeah, so we've got the ticket class, all passengers, and passengers missing cabin and age information. What can you kind of infer from that, Jason?
Well, what I see is that when I look at all of the passengers, I do clearly have more third class cabin or third class tickets, but it's not. It's a little bit more than the other two combined. But when I look at the passengers with age missing, there's a lot more third class. So what it tells me, I guess, is that we didn't capture as much data on the third class cabin, on the third class passengers. We didn't tend to collect their age.
Yeah, excellent. So, and that might have just been a byproduct of how they bought the tickets, essentially. Yeah, I buy a ticket.
They didn't buy
like
them online.
They didn't buy. No, I'm pretty sure they don't. There wasn't a Groupon or anything like that. Okay, that's fine. All right. Well, moving on. All right. So we've got those tickets, and we want to watch out for values where missing values could be represented in a different way. So some values might actually be entered as 0, but it's not actually 0 that they're representing, right?
Yeah, I mean, this goes back to what you were saying earlier, right? Where somebody might type in the string NA. Well, another thing, if they didn't know the value, you could easily imagine them doing is typing in a placeholder. And I mean, if 0 is probably the most obvious placeholder, if it's a numeric field and they don't know, so they hit the 0. And of course, that's going to mess with our data. So we've created, I think, yeah, we're creating essentially a fake data set where instead of null for age, we're going to see what would happen if we had 0 in our what are really the null values, or the ones that we don't know. What would happen if we had 0 there instead?
Well, let's go ahead and run that cell and see it. So the average age on the ship was 29.69. That's if we had the data for them. But if we made the ages 0, that average age would drop down to 23, which is not really representative, right? If we go back to that term from before.
Yeah, so one, obviously Pandas is doing, when we just do the mean method here, obviously Pandas is doing a great job of ignoring the null and just doing an average on the data that we actually have. But when we replace that with 0, well, then that's a valid number. So now it's going to average, including that 0. And when it does that, it's skewing our data. And worse, if we look back and think about what we saw in that histogram earlier, that bar chart with the buckets, we saw that third class was much more likely to not have age. What that means here is we're actually, if we had 0s in that age, we're actually skewing third class a lot more than we're skewing the other ones. So we're creating, it's not just bad data, but we're creating poor representation of our population as well.
Okay, good. Very, very good point. So let's go ahead and actually visualize this. So if we look at the data, you can see that chart is showing a large skew on the left with age, not representative at all. We should see a normal distribution typically when we look at that data, or we'd expect to from an age range. That would be my assumption. So
I mean, maybe some modified normal distribution, of course, because maybe some people are more likely to travel on ships at certain ages. But what you certainly, so maybe a left skew or right skew, you certainly wouldn't expect to see that weird bubble at 0.
Yeah, it'd be like, no, why are you transporting so many babies? That would be the question I'd be asking, right?
That's a very good question. That is very suspicious. That's an awful lot of babies on your ship, sir.
All right, so we've got some issues with missing data, and we need to look at some of the options for it. And like you said in one of the slides before, there's actually a few options we have. We can delete data with missing rows, and that's actually a pretty popular method, and it's got some advantages, right?
Yeah, I mean, of course, if you have enough data to do this, then you're by getting rid of the data that's not clean, you remove all skewing. You're just saying, you know what, this isn't good enough. It's not representative. I'm just going to remove it.
Right. Cool. So if we look at what we're doing here, we'll just drop the data set where they've embarked, reindex it, and then print the shape for the data. So in this case here, that was just working on the embarked, and it went down to 889 records. So yeah, a little bit of a cleaning effort, not too bad. Now the other option is to replace empty values with the mean or the median for that data as well. So we don't want to replace the age with 0, but we want to find out what the average age is and replace the missing ages with that value, so it doesn't affect the age value when we look at the data. It's a little bit more representative.
Yeah, it's certainly better than filling it with 0. This is still going to skew our data. We're using a global mean, and I think, as you pointed out when we discussed this at one point, that global mean might not hold for other, say for a certain gender. It might be a different average age. For male and female, you might have different average ages. But then the problem with kind of covariating with the fields that are correlated is we are training a machine learning model eventually. We haven't gotten there yet, but eventually that's going to find the correlations. And especially once we get into a deeper model, deep learning models, which we're not doing admittedly during this class. Once we get into deep learning modules, it's actually very good at finding the nuances and the twists within with those correlations. Less so with the linear models. They're not necessarily so good at. So if you're truly just doing linear regression, as we've done in most of our examples so far, you may be okay kind of cheating it and saying, okay, I'm going to get the mean of the males and the mean of the females, or the mean of the first class and the mean of the third class. You can play around with it, but there be dragons, as they say, right?
Yeah, there is. And look, I've when I was doing some statistics probably 6 months ago, some of the packages I was using there was trying to solve that for me, and it's actually a much more complicated issue than we're doing some simple processes on this data to clean it up. But I want to go to our questions, for example. We have one here. In the case of ages of 0, it's fairly obvious that is bad or not clean data. Are there common strategies to find bad data that isn't so obvious?
Unfortunately, it can be incredibly difficult. But certainly looking at your histogram or that bar chart where we were kind of looking for a distribution that we would expect, that's your number one tool. An example that comes to mind of what we're talking about is that it's not very obvious. Is I know that when I go to buy alcohol at the store, they'll look at my ID, but then they don't actually bother. The computer expects the cashier to input my birth date, but while they'll check it, they often won't bother to actually input my real birth date. They'll then go, as soon as they look at, they'll just go 1/1/1970, 1/1/1980, whatever habit they have. They have some keystroke muscle memory, and they'll just enter that in. Well, those datas are not automatically or obviously bad until we look at that histogram. And you look at that histogram, no matter how you bucket it, if everyone's doing that, you're going to see some bubbles. You're going to see some lines that are just too tall. And from there, maybe you have to actually start to figure out individual cashiers and their patterns. That, it can be difficult. It's why most people will tell you that data prep, data cleaning is the most time-consuming process by far of doing machine learning. Although interestingly, I just a little aside here, people who come to machine learning, who come to data science from, say, from academia or from just coming straight out of school, they're often very surprised by how much effort has to go into that data cleansing and that data prep and that data work. To be honest, as someone who had a long software engineering career before going anywhere near machine learning, it was just par for the course. You have to clean data to display it on a user interface correctly. You have to clean data to do any sort of math or aggregation on it. So it should be mostly par for the course to understand that that's part of the work. That it is at a little bit of a different level and a different kind, where you have to more interested in patterns than maybe just raw cleanliness, but it's part of the overall software engineering task as well.
All right, good. So there's a follow-up question from it. So you suggest looking at the data points and investigate outliers. I think that's a pretty good, reasonable approach, right?
Yeah, I mean, honestly, that's the entire class today is all about looking at our data points, looking at what we have, trying to find the outliers. The individual outliers, I mean, if we just look at, we're going to do that in a little while, look at individual outliers, but also the trend outliers, like we talked about, look at the histogram and see that while the actual data to each individual data point looks fine, the fact that there are 5 times as many people with a birth date of 1/1/1970 versus any other birth date, none of those individual records are an outlier. But the the trend in the data is certainly an outlier and is certainly an issue.
All right. Well, let's move on. So we changed the mean age to, the missing age cells to the mean age. And if we look at the data here again, we'll actually see that there's now no missing age entries in that data set. So that's not too bad. Now, our third option, our final option for this exercise, is to assign a new category to unknown categorical data. So where we've got some missing data, we create a new column that says, yeah, we have missing data. It's called unknown in this place here. So
yeah, just to clarify slightly, I think you're maybe almost jumping ahead to our next exercise because because right now, actually, all we're doing is filling in where it said null before. We're filling in just the word unknown.
Yeah.
And that actually by itself isn't helpful. Right. So that it's not helpful yet. We're going to see in a little while, folks, how this actually becomes helpful and actually layers in with what is a more accepted approach, almost whether it's categorical data like this or not. And that is to have an entirely new, what Glenn was just talking about, having an entirely new column, a separate column that just says, you could say, is cabin null? You might have I have a column that says, is cabin null? And it's a yes or no or a 1 or 0. Meanwhile, cabin just has some data in it. It might be numeric. It might be non-numeric. It could be helpful by itself, or it could actually be irrelevant by itself, but the is cabin null column becomes useful. And that actually is something that by doing what we just did here, some of our other techniques are going to make that automatically happen. We'll see that in just a couple minutes.
Yeah, awesome. So that's our 3 techniques we've looking at. Basically just doing some basic data cleaning. If you've done any database work, you're probably used to these slight pain points when you're going through the data, but it's essentially to make sure that the data we have is in a really good shape. So we'll get the slides over to you now, Jason, if you want to take control.
Yes, I'll take control. However, you have to ask me some questions.
You know what? I think I can get that done. That's fine.
First, let's have head over to that URL on the screen so they can answer questions as well. So it's not just me.
Yeah, we want to see what your answers are. In fact, as you type in your answers, we get to see how many people are responding as well. We look at our own data for this. That's good.
Yep, so it's aka.ms learn live TV, aka.ms/learn live TV. Here we go.
All right, so our first question for the day: why do we clean our data before training? Is it A, removing rows of data makes our model more powerful? Is it B, cleaning data helps us select features that will be helpful for our model's performance? Or C, removing rows that have errors prevent these from misleading the training process? What do you think, Jason?
So removing rows of data makes our model more powerful just doesn't sound like it makes sense at all. So we'll move on from that one. Cleaning data helps us select features that will be helpful for the model's performance. You know, I actually don't hate this answer because while it says cleaning data, cleaning and data analysis are kind of hand in hand, and data analysis absolutely will help us select features. So I don't hate that answer. But removing rows that have errors prevents these from misleading the training process. That's a better answer. So I'm going to go with C.
C. You know what? I think almost everyone has gone with C as well. Yeah, almost probably about 90% of the people have gone with C. Excellent.
Yes, fantastic. Good job,
folks.
Paying
attention. Nice. So let's move on to the second question, the last one in this little set. What is a data sample and what is a population? Oh, I love this question. So response A, is it a sample is all possible data we care about. A population is a subset of that data which we actually have on hand. Is it B, both population sample mean data we train our model with? Or is it C, a population is all possible data we care about and a sample is the subset of data which we actually have on hand?
All right, so is a sample all possible data we care about? Right off the bat, I'm going to say no. So our next option, both population and sample mean data that we train our model with. That's wrong. A population is everything, and we don't have everything. We can only train with data we have, which we don't have. The population is the entire universe. So, and that's actually what C is telling me. A population is all possible data we care about. A sample is a subset that we actually have, and therefore that we can do our training on. So yes, C is going to be our correct answer, and 100% this time. Our folks out there nailed it. Well done.
Absolutely. Cool. We've also got a question from before. We might have missed that one. Should we have used a bar plot given that P class was a categorical variable? I know it works now.
This is going to go straight to what I said about there being so many different options on how to visualize things, and we actually will be looking at more visualization options in our next exercise. In fact, that's most of what this entire session today is about, are different visualization options. So yes, you can. In fact, using the histogram is also even sort of a shortcut way to give us a bar plot. We can use histograms differently with continuous variables as well. But yes. I mean, the short answer is yes. That's a great point. That's something we can do. We actually will do it a little bit, but there's so many different ways we can look at our data. So many different ways we can slice it. That will all give us, well, each of those will give us some insight into our data.
All right, so we need to move on and have a look at the different types of data and what we can do here.
Yes, so that question actually led us into it wonderfully, right? Is some of our data is categorical. Some of our data is what we call continuous. The reality simply is that we have a lot of different types of data. Each needs to be prepped and each needs to be analyzed slightly differently. So let's touch on each of the major broad categories first. So when I say continuous, and I've said that a few times, what I basically mean are those type of numbers that can achieve kind of any value between say 1 and 2 or 0 and 1, right? The point is they're not integers, so it's not just 1, 2, 3. It could be, the value could be 1.00001. So age is an example. I'm not just X number of years old. I'm not just 44 years old. I'll just go ahead and admit it. But I'm 44 plus some days, right? And so that can be represented as, 44.7 or 44.74, right? There is a continuous spectrum of values to that. And same thing with height, same thing with a lot of different values. But the number of apples I possess, unless I can, or maybe the number of apples I can sell, unless because I can't sell half an apple, that would seem like it might be a health issue. The number of apples I can sell, that is what we call ordinal data. It is either ordered or it is strictly integral. That is an integer. I can have 1 or 2, but I can't have 1.2. So we have that ordinal data. Those are also numeric. Now, categorical data is a weird beast because a lot of times you'll see these represented numerically, but we're going to see why that can be a bad idea in a moment. And finally, IDs are things that can be like strings or GUIDs. These are not really useful data. They're not going to have a correlation. Someone's first name, well, I guess their full name or their ID number, a GUID. None of these things have predictive value, but we might still sort of need to keep them aside and hold on to them so that we can correlate data later, so that we can correlate it to a record in our database later.
Yeah, but you wouldn't normally use the IDs in your training set, right?
Exactly, because they don't have predictive value. But if you put them in there, the libraries are going to try. They're going to try to fit them. And if you let it train long enough, or if you give it a complicated enough, if you're messing around with deep learning and you give it a complicated enough model, it will find something it believes is a correlation with that GUID or that first name field. It'll be wrong, but it'll find something that it thinks is a signal.
All right.
And of course, for each of these, we have data types. If you've done any programming, you're probably fairly familiar with the fact that we have certain data types like integers that we would use for whole numbers, 2, 4, 5. And we have things like float and double to represent our continuous values, like 2.43 as we see on the screen. Strings are things that we don't really treat those almost more as IDs for right now. There are some complicated techniques we can get into in deep learning for things like natural language processing, but that's definitely outside the scope, because first you have to do serious pre-processing to turn those into numeric representations. Of course, Boolean, null values, we get it. We don't need to memorize that slide. That's not the important point. The takeaway is that we have those different types and those same sort of things we can think of. Alan, you are so on point. Alan's asking a question about years and dates, and look at what my next slide is talking about. Well done, sir. So actually, let's focus specifically on dates, and then we'll broaden it since you asked the question, Alan, and then we'll broaden it out to the bigger topic of derived data types. But even in the sense of what I talked about with text, sometimes you have some data, but it needs to be turned into something else, transformed, handled in some way to turn it into something that can be mathematically represented. So let's look at the example of the date. If I have a string date, 1st January 2017, or I have 3 different fields, 1st January 2017, in all these cases, I have some sort of problem. If I have a field of day of month, and then year, we know those are not independent variables, and actually that is a key phrase on the statistics side that informs machine learning. So independent variables, they are not independent. The day of the month is critically tied into the month, and that is critically tied into the year. These are all inextricably linked. So we do want to combine those. Now, the easiest way is this example that we see right on the screen. We can just mash those together as 2017, 01, 01. That'll work. That does fit into a number field. And we'll usually get a fine amount of success doing that. But Glenn, what problem do we run into if we just mash the data together that way?
Yeah, I think it's not really representative. You'd probably want to use something like, I would use something like the number of days since 1900, for example, in integer parts, and then you could portion it, and you get this continual line going up, and then that would be more representative of what the dates are used for.
Yeah, so that's a great idea, like the number of days or some time period since a fixed point. Another approach we can even use 2017 and then say the percentage of 2017 that we're through, or whatever. So we're at 2017.5 would be July 1st.
Yeah.
And the advantage that we get with this section is just that, or this technique is that it's continuous. With 2017 0101, our machine learning model might at some point try to, and it would try to deal with then what is 2017 1515. Well, it's nothing. It's not valid. And so if we can keep things, if we can cast things as valid ranges, we're going to be a lot better off. Okay, so that's what we're going to do in our next exercise.
All right.
We're going to play with some of our missing data. In particular, we're going to deal with it type by type, category by category of missing data, right?
Yeah, that's right. So like you can see on the screen, there's a few things that we're going through. We'll first off inspect the data, and we'll visualize the ordinal data, the continuous data, as well as the categorical data. So hopefully you can see my screen. I'll make sure Jason's image is out of the way so no one's seeing that. And if we just scroll down here, like in most of our exercises, the first thing we do is just inspect the data that we have, and we'll look at the first few rows. This is no different to what we did in the previous exercise, really. Just go ahead and run that. Scroll down, and again, we can see the data that we're working with. No different, really, at this point. So we want to look at some of the other structure, and in fact, just look at the summary of the data as well, and look at the data types. You went through the data types in one of the previous slides, but we can have a look at things like the passenger ID that's stored as an integer. If we look at name, sex, that's stored as an object, which is really a string representation in this case.
Yep. So yeah, if we don't have anything too crazy going on in our data sets, usually if we see object, we can say, oh, I think that's a string.
Yeah, cool. And likewise with the age or the sibling or spouse. So the sibling or spouse, that's actually some categorical data, which is it's actually probably closer to a Boolean representative or number structure.
No, yeah, that one. So those ones actually are the count. Those ones are actually the count of siblings, or the number of siblings, or number of spouses. So yeah, that actually integral holds well for those. This would be ordinal, yeah.
Cool. All right, and we go through it, and the parch ticket, that would be an integer. The ticket would be a string typically.
We're gonna work through them in the actual in the actual code, so we don't need to break down.
That's all right. That's all right. I'm jumping ahead of myself there, but we are looking at the same structure, looking at the ordinal data, the continuous data, and categorical. We'll start with the ordinal though, as well. So the P class, the ticket class, the parch, and the siblings and spouse. So if we go ahead and
let's even talk about why is P class ordinal, because that one we could easily confuse with categorical, because it's not a count. It is what class are you in? And if that was some placeholder value or some arbitrary name, like the way we name meeting rooms in the tech industry or something like that, then it would be just categorical. But we are pretty sure that first class is in some way better than second class, which is in some way better than third class. So there is a logical ordering to it. And so it is our belief as the data scientists or the data analysts involved here, it's our belief that we're better off treating it as an ordered set rather than a categorical set. Well, that's certainly something we could experiment with and play with and validate.
Yeah, we'll look at some cases where that's not the case a bit later in the exercise too. Right, awesome. So let's have a look at that data. Look at the P class. And we're actually seeing that we've got the class down the bottom here and the average number of survival, or the survival rate from 0 to 1 in this particular case. We've also got a box plot going across to the right. Now, what would we infer from this chart here?
Yeah, so the main chart here is telling us for everyone in a given class, first class, second class, third class along the bottom, what's the chance they survive? So we can see that if you were in first class, you had a 60% chance of survival. If you were in third class, it's something like, what, a 25%. Yeah. And of course, that's for the 1,000 records that we do have. But that box plot up at the top actually shows us, though, that more than half of the records are third class records. So we see that because in the box plot, the median is going to have a line, which is actually vanished at the bottom or at the far right side. It's also going to have a far right edge, which is combined with the median. And then finally, we're going to have that far whisker. So basically our 50th percentile, our 75th percentile, and our maximum or 100th% record all are in third class. That tells us more than half of the records are in the third class bucket. So the vast majority of our folks were in the 25% survival rate likelihood.
Awesome. All right, well, let's have
Not for them.
Yeah. All right, so let's have a look at some more visualizations of data again. Well, this time we're going to group it by the ticket class as well. So we've got the P class, we've got the survival rates. I'll just scroll that up a little bit. So we're coloring by the number of parents or children as well, and the likelihood of survival.
Yeah, and in a sense, this is the same graph, but we took each of those columns and then shredded it out further and color coded them by whether or not you had a parent or child with you. Now, unfortunately, we don't know if it's a parent or child. So to the extent that parents who have children also have children that have parents, I would wonder if that means that we are double counting. In a lot of cases, that would be a thing we'd have to look into. But either way, it's interesting data. It's interesting to see that for first and second class, these larger families are much more likely to survive.
Yeah, and they used to have a model where the children were specifically looked after first as well at that time. So it kind of makes sense historically too.
Yeah.
All right. So let's scroll down again. We're running tight on time here. So if we look at our structure again, we've got a box and whisker chart here for the various classes, looking at the data set, the P class down the bottom, and the number of siblings on the left and right. Well, sorry, going up the y-axis.
Yeah, and here we're just seeing that really the vast majority of folks did not have a sibling or spouse. So that was a sibling or spouse field. The vast majority of folks, more than 50%, didn't have either. And in general, there's not much to see here based on the distribution of sibling spouse compared to class.
Yeah, but if there was a relationship, you'd be able to see it in a little bit more detail, which is nice. All right. So in this case, let's have a look at the continuous data again. So remind everyone what continuous data is, Jason.
Yeah, again, this is the data that can basically take any value between two numbers or any value of numbers, any amount of precision, if you will.
Right. So
your floating points, your doubles type of data.
Yeah. So things like the age and the fair.
Yeah.
In this case,
we can use histograms or bar charts for these as well. We would just bucket them, and a lot of times that can be super helpful. But the scatter plot that allows us to see kind of that full continuous range charted against each other can do some amazing things with visualization, letting us see patterns. As we know before in our other modules, we used these to visualize what our eventual linear regression line would actually look like.
Yeah, so we're not looking at the survivability here, but we can certainly see that most people actually didn't pay a huge amount for the fair, but there were a few that did in particular. So we can see the kind of the clusters of things around the bottom here. This is where the majority of the tickets were bought, and also the age dispersion as well. But there isn't a direct relationship between age and fare from that. So does the cost of a fare or a person's age have a relationship with the survival? It's a good question. So we can draw some charts here and take a look at it. So we'll first off look at the fare versus the survival rate, and then below, I might shrink that a little bit, and then look at the age versus survival. So if they paid more for the fare, how likely were they to survive? So in this case here, if they paid more than $500, and there's really only
a single data point. So that's that one looks a little bit like something we'd probably ignore. But the left-hand side of that chart is super engaging.
Right. So if they've paid, kind of the majority of people here in this case are unlikely to survive, like 0.4% out of 1, and you can see the trends of that as well for the fare costs.
Yeah, to within a reasonable amount, and actually almost completely true, because you only have a few outliers left after the pattern breaks down. So it looks really compelling here that even past our whiskers on our bar chart there, we still see a strong correlation. You pay more likely to survive.
All right, and a similar thing with the age versus on the bottom here, we can see the demographic here. Most people are between 20 and roughly 38.
Yeah,
that's the majority of people. So the survival rate.
But we're not seeing the strong correlation except amongst the children, which goes to your earlier point that the children are more likely to survive, or we're more likely to be taken care of. However, they that broke down once we got to about 10. So apparently, once you're 10, you're on your own, I guess. I don't know.
I love it. All right. So that's a look at our continuous data. Taking a look at our categorical data, we've got things like the gender, where they embarked from, and the cabin, and the survival as well. So survival is just 0 for no and 1 for yes. For example, the embarked is the particular port where they got on it, and does that have a correlation as well? So we've got some code here,
and let's talk real quick. That port, right? That's clearly not going to be ordinal the way class was. So when I said class is 1, 2, and 3, clearly class 1 has some meaningfulness of being better or more than or less than. Either way, ordered against 1, 1, 2, 3 has some logical meaning, but CQS doesn't. We don't want to alphabetize that. Those are just labels.
Right. So looking through the structure here, we want to apply that. So for things like the data structure, we want to do a few things. I'll just run this straight up. You want to talk us through the code on the screen, Jason?
I mean, as you pointed out, we're running a little low on time, but what we're doing is creating a couple plots, and let's just go ahead and look at it. It's to be honest, the graphing code is not the most interesting thing. They can always look up how to do it later, but it's for this one, it's a little bit dense, I guess, that the graphing code, but we can see that we can get creative, and this is what we were talking about earlier. So using color, or using plot size to start visualizing additional dimensions. So with a 2x2 graph, a 2-dimensional graph, port versus gender here, we really only have that 2-dimensional view. But by adding a color dimension, now we can get the survival rate. And by adding a size dimension on those dots, that size represents the number of passengers who, for instance, that giant purple are people who got on at port S and are male. So that is giant, meaning the vast majority of people on there that we have data for are males who got on at port S. And then the vast majority, or the best survival rate, is amongst females who got on at port C. So we can see that based on the coloration. So despite having just 2 dimensions to play with in our chart, we were able to use color and size to enrich the visualization we were able to get out of this.
Yeah, and looking at the data, there's certainly a lot more men on the ship, or a lot more data about men on the ship as well.
Right. We do, of course, have half the records missing, so there's always that, and that is, of course, a concern for representativeness.
Exactly. Yeah. Awesome. So that's our look at essentially visualizing the ordinal, continuous, and categorical data. Let's jump into the next section.
All right, taking it back over from you.
All right.
One-hot vectors. All right, what does that mean? That's kind of a cool phrase at any rate. One-hot vectors have to do with categorical data. So let's talk about categorical data again, the C, the Q, the S. If we were to assign, or actually, let's not even talk about assigning numbers. If we were to just alphabetize C, Q, and S and treat that in a graph as if it was supposed to be meaningful, we would get very bad data. And same thing if we did try to assign a numeric value to it. If we assigned C as 1, Q as 2, S is 3, which is the sort of thing we might do in a database, or really in any kind of data store, is a reasonable thing to do, because we know we're also then, we or someone who is going to write imperative code is also in charge of how to handle it. So we're not going to add two of them together or do anything mathy on those token values, right? That 1, 2, and 3 just represents a token. However, when we want to feed it into our machine learning model, we need to give it something that is sufficiently mathy, for lack of a better term, that our machine learning model can do whatever it needs to. That our machine learning model can treat those as numbers when we give it numbers and rely on truth, for some value of truth, to come out the other end. And we can see actually pretty easily here. Let me get that laser pointer going. We can see if I sort CSQ by my class, and I'm just trying to chart something, it doesn't matter what I'm charting against, because the point is, if I take the port as a number, and this is 1, 2, and I've assigned it 1, 2, and 3, and I try to do a regression or a trend line, that's what I'm going to get, something like that. But that's an arbitrary 1, 2, and 3 was arbitrary. If I renumber so that S is 1 and C is 2, I get an entirely different linear trend line. And this is what I'm predicting against. This is what I'm using to forecast other values. So obviously we can't do this. Obviously this is completely wrecking our data. We can't do that. We can't treat this as a number. The solution is to actually give each of the potential values its own column. And then each of those columns is simply a Boolean. And that Boolean, so we say, okay, well, is it shortboard? Then that was the C. If it's a C, in the original column, the original data was a C, then this new column becomes a 1. And these become zeros. Same thing if we had a Q.
But I would find, I actually really love the one-hot encoding, but in this particular case, it kind of infers that the first port there won't affect the second or third port using this structure as well when the machine learning data is being used. It will not to a greater extent as if you had it as an ordinal or continuous value.
You're right. You're right. To the extent of what it actually touches a little bit with what we talked about earlier, the concept of independent variables. These are not entirely independent variables. They're not entirely independent of each other, because we know that we should not have 1 and 1. And that is going to absolutely affect what we call our statistical power. And it's not by any means the only thing that is going to affect our statistical power. If we remove a lot of rows, obviously we don't have much data, then our model is going to lack statistical power or the ability to generalize to the greater population. So removing rows obviously does that, but having a lot of irrelevant columns also does that. Having a lot of covariant columns, in other words, they're not independent of each other, and so when one goes up, the other goes up as well, makes it hard for our training model to adjust the weight of one without it throwing the other one or adjust the parameter of one without throwing the other one into a tizzy. So yes, you're absolutely right, Glenn. We're not creating a perfect data model when we do one-hot encoding. We're creating the best one we can.
Yeah.
Of course, we talked about not just one-hot encoding, but there are a number of things that can lower our statistical power, like removing data, having less data, less rows, obviously. Worthless columns we talked about. And of course, we mentioned the one-hot encoding, even though it's the best solution most of the time for categorical data, the vast majority of the time for categorical data, it's the best solution. There are some trade-offs. And in fact, we will look at how to handle one of the trade-offs in this next exercise coming up, because one of the things that can happen is if you have, when we talk about categorical data, to those of us who are familiar with data modeling in, say, a SQL Server or a Postgres, you'll be familiar with the idea of a lookup table. So your categorical is that, that stuff that's in a lookup table. But if your lookups have 200, 2,000 potential values, it's product type, and you're that big online retailer that remains nameless, then you've got a lot in that lookup type, in that lookup. We'll use the other big online retailer, Walmart, who happens to be one of our great customers. So your product type for Walmart is going to have thousands of values in it. We don't want to turn that into a one-hot encoding because of Glenn's point. Because when we create these extra columns that are not properly independent, we are eroding our statistical power. We're eroding our ability to create a model that generalizes to all of our population, because it's just harder to fit when you have, like, again, one column that we have to adjust the parameter of. Remember when we talked about bias and slope, we have to adjust that slope, and then that affects the other one because they're not properly independent. So it's definitely something that causes problems for our models. Let's see how we can handle actually several of those situations, including the one I was just talking about, in our next exercise. Mr. Stevens?
Yeah, so let me switch over. And there's a few things that we're going through here. I'll just share my screen. Hopefully you can see that very soon. But we'll be looking at training the model, and we'll look at the various things that we can do to improve the statistical power as well as we go through. And we'll obviously do the one-hot vectors as we go along. Hopefully you can see my screen here. And we're going to look at that categorical data, see what we can do to restructure this. So, and there's a few things we're going here. I know we're pretty tight on time. So like most of the parts of the exercises, we'll read through our Titanic data. We'll fill the cabins that are null with the term unknown, and we'll also drop the records that are missing age information here, and then drop some of the columns as well, and then just display the head of that structure. So we've got a kind of a new shape to the data. So obviously some less rows and less columns in the process.
And yeah, and importantly, we did that unknown again right there, right? So in that one categorical column, we added unknown where it's null, and that's going to become important in just a moment.
Cool. So we'll be training the model here as well. We'll just go through it, and we want to look at some of the numerical data first. So just the number features. I'll go ahead and run that cell. Well, I've just gone dark here for a second.
We got you.
It's very early in the morning. Just give me 2 seconds.
I think your camera was compensating well.
Wow, it's 8 o'clock. We are so live here. It's 8 o'clock in the morning. Our lights in the Microsoft office here just went off a little bit. So we have the features that we're running, where we've got age, B class, and so on. And we want to train this logistical regression. Now, did we mention the term logistical regression before, Jason?
Yeah, actually, so we're gonna talk about that in depth in 2 episodes. But right now it's very similar to linear regression, except instead of trying to predict a continuous value, we're trying to predict basically one of 2 values. So basically think of it as yes or no, black or white, true or false, right? So logistic regression is essentially predicting a binary, if you will.
Right. Cool. And so we've got our details here, but we're also showing the cost as well. We'll be measuring the cost as we go through, right?
Yeah, and we've only inputted 5 features so far, and I think they're all well, there are a few continuous features and a few integral or integer features. But yeah.
Right. Cool. So moving on. So we've got our categorical features. So we're going to convert the gender into is female. Whoops, and just make that 0 for male and 1 for female, and include that in our model as well. So that's our additional column we create, and we're just replacing the values here. Male has 0, female has 1. And then we'll look again at that data, training the logistical regression using the new features, which includes that is female column, and then again show the cost of that process towards the end.
And we're not including in our features for prediction here, what we're not including is that original text column sex. Instead, we're only including the binary is female, which is just yes or no or 1 or 0. So that's going to have that's going to be usable actually, which is something that our text column wouldn't have been.
Cool. And there's our columns across, and actually extends to a new display below, but essentially it's still the same structure. There's the record ID. All right, and if I scroll down, we can see the new cost here, which is 0.47. If we equate that, that's certainly a lower cost than what we had before, Jason.
Yeah, obviously that's much better. That's because the male versus female had a lot of predictive power. It was really relevant to that survival rate, as we saw with our data analysis earlier. So now that we're training a model with our cleansed data, and we used the male female feature, we can see that it really improved the predictive nature and finally got us above pure chance.
Good.
We're now slightly better than pure chance.
Yeah, but our aim is to be better and better as we go along. All right, our next step is the one hot encoding. This is where we've got the ticket class as an ordinal feature, and we want to restructure it so each of the class values become their own column that we can use. This is the one hot vector that we were discussing before. So if we take a look at what we're doing here, there's actually some nice mechanisms here. The method in pandas is a little bit odd when I look at it. I got to be honest. They get dummies. Yeah, get dummies. But essentially what it's doing is getting that P class and then just creating individual columns for each value that represents it. So
yeah, it looked at all of our rows and saw that the only possible values were 1, 2, and 3. And so it went ahead and created a P class 1, a P class 2, and a P class 3 column, and it did the populations for us. So we can see if the original P class, it's tacked back on at the end there again. The original P class was 3, then the P class 3 column has 1. If the original P class was 1, then P class 1 has a 1. So we've just turned it into a bunch of binary columns, as we talked about.
Right. Cool. Now, if we want to look at that new data set as well, we'll list the features. We won't have that P class added like we did before because we don't want that to affect it. And we'll run that through the logistical regression and see what number we get. So 0.47 and 1.7, slight improvement anyway.
Actually, that's slightly worse.
Ever so slightly worse?
That's okay. We still got things to do left. Yeah.
Well, yeah, it is, isn't it? Right, cool. So we've got one more, which I think we're doing with cabin as well. And it's a similar process. We'll get the dummies for the P class and cabin. And go ahead.
Interesting though. Yeah, go ahead. Let's run this real quick.
Why do you think it's interesting, Jason?
Well,
talk to me.
Because there's a lot of cabins. Notice it says 135 cabins found. So that's a lot. We've just added 135 columns. So I can see that it did actually improve our predictive value of our model a little bit anyway. So hey, good for it. but 135 is not ideal when we've 135 new columns, imputed columns. We've already got a bunch of other columns. So now we're looking at like 200 columns when we only have 900 input records. That's not a good balance. We really don't ever want our column count getting anywhere near our row count if we're going to be able to provide enough data points on each column to actually allow our model to figure things out. So here we get a little creative. Next, we get a little creative with that. Instead of just taking the raw cabin value,
we get the deck, right? So rather than go, here's the cabin, let's actually just simplify that to the deck, and we'll probably have far less values than that 135.
Yeah, and this might require a little bit, of domain knowledge to know this, but to know that it's the deck specifically. But you certainly, if you look at the data, you'll see that cabin looks like A underscore some number, B underscore some number, and given that, we can at least infer that there's a possibility that just grabbing that first identifier, that A, B, C, and then grouping by that or bucketing by that might be a better approach. We might not know that it's correlated with DEC, but it's certainly the sort of thing that we'd want to try just when we saw that data pattern. We'd want to try splitting that up. And when we do, that's exactly what we do. We are now just creating a few extra columns.
Yeah, but I imagine you'd want to run experiments like this to see which ones actually improve the statistical likelihood or the reduce the
All right,
cost.
let's run that last cell and show them the final results, and then
excellent.
Gotta wrap
So
things up, don't we?
That's 0.45 there, and the last cell is really just a summary of all the methods we've tried here. So I've got it down from 0.61 to 0.45. Good improvement.
Yeah, so still not an amazingly predictive model, but of course we don't have a lot of good data, and we're only doing a linear model here when we know that there's a lot of dependencies and nonlinear trends like age being relevant, but only until 10. So there are things that are definitely we can expect a linear model to not quite be ideal, but we've done some good work. All right, let's hop back into our slides then, in order to get ready to say goodbye. So we focused on, well, we already know what are data, although I love that we're grammatically correct on this slide. What are data? How to get our data sets to being good data sets and how to decide if they are. And really just the thought process we go through and the analysis process, visualization process we go through for all this. So we've looked at all that. Not to forget, we have quite a few other classes, other sessions coming up every week on Tuesday. Make sure you're joining us every week at this time. Our next one, we're going to finally dive deep into the nuances of regression models, and not just look at one or two simple regression models. We're going to get a lot more into it. We're going to use a lot more features, see how they affect the outcome. Good stuff.
So we've done some of the foundational work in those first three, Jason. It starts to get a bit more intense.
It does
from here. Yeah.
It does. Good stuff though. Yeah, it's intense, but it's not scary. But you're going to walk away really feeling like you have new aha moments every day. All right, remember, you can go to aka.ms/learnml/data to go through this content again, to do the coding exercises for yourself. Remember, just like Glenn added a code block here or there as he needed to, you get to do that. You get to change the code without having to actually install anything or have your own computer or anything like that. It all is just there for you in the browser. And finally, the reason that we're rushing right here at the end is because we had an awful lot to say about data analysis, data visualization, and yet we still only scratched the surface. And I'm actually really excited about this because they're not even launching it till tomorrow, but our Cloud Advocate team has been working on a huge data analysis content package that they have allowed us to mention early and give you the AKA. So aka.ms/data science beginners. This is really focused not on ML style data science, but the data analysis, data visualization, kind of the statistical underpinnings of data science. And that's just hugely valuable for anyone who does want to do machine learning. So once again, they weren't even officially launching it till tomorrow. But when I said, hey, we're doing a data cleansing and data prep class today, could we let people have access? They said, sure. So there we go. aka.ms/data science beginners is going to let you dive deeper on topics like this. For more about machine learning, the rest of this learning path and its sister learning paths, which are linked right there. And then Cloud Advocates, once again, hard at work on some more cool exercises. So they've got some beginning ML stuff as well. And this content is definitely complementary to what we're doing here. It's going to focus on using a lot of different libraries, going through a lot of different sort of scenarios, and approaching different sets of problems. So good stuff there as well.
Awesome. So I think our next slide, we've probably got time, if I look at it, maybe for 1 or 2 questions, if they're coming through.
Yeah, that'd be great. Is there 1 or 2 that we could maybe handle to my moderators?
Our moderators are just power people, and they've just answered.
I know they're just answering everything, I think. Yeah.
Yeah.
All right. If we don't have any up there right now, then I think we'll wait 30 more seconds. We'll just go like this.
Yeah, we do have a buffer, but that's a really good resource. Thank you to the Cloud Advocates for that previous one for the data science for beginners.
Yeah, it's definitely fantastic. I was really excited that they were able to get it buttoned up enough for us to announce it today. Yeah.
Okay. Well, cool. Well, feel free to come back the following Tuesdays as well. It's always useful to actually ask questions when you're going through a process and get it verified as well. I can see some comments there. Apollorus said, "This is pretty cool. Thanks for taking the time to do this." No doubt. We'll take some more time over the subsequent weeks as well. Hope
That's
you
right. All the way
join us
till
again.
mid-November, we're doing this.
Yeah. There's a great question here as well. How can we apply machine learning in data cleaning?
The answer is carefully. If the idea is to make your data an input to other machine learning models, in general, I wouldn't go too far in using simpler machine learning models and then feeding partial results into a later machine learning model. While complex models do involve several steps, you at any given point you have to be really careful. Again, there be dragons. For instance, when we talked about those covariants, right? So even looking at a spreadsheet of data and seeing that age and gender tend to be correlated, we're going to potentially drop the predictive power or the ability of our model to generalize if we cheat on those things. And if we apply say we apply that, just like a correlation actually really is a very simple linear model. If we apply that, we're going to create things that'll ultimately trick our later model. It's almost better to let our later model figure that out for itself. Now, Hal wants to know, can we explain more about logistic regression and cost in logistic regression? And the answer is yes, we can, but in 2 weeks.
Yeah.
Right? Or you can always go to the module right now.
All right, we're down to our last minute, so we have to say a nice fond farewell to everyone that's joined us. Come back and see us next week. Thank you for coming, and we'll see you then. Bye for now.